Welcome to the presentation on the operational amplifier. The operational amplifier is often called an op-amp and is drawn as a triangle in a circuit schematic. Op-amps are used as buffers, amplifiers, summing amplifiers, integrators, active filters, function generators, and converters. Op-amps have differential inputs, meaning that they have two inputs and they will work on the difference in voltage between those two inputs. As far as outputs, they could have a single output or a differential output. They use feedback to control the relationship between the input and the output. And most op-amps require a bipolar power supply for proper operation, but they may be possibly configured to work from a single power supply. And they are called operational amplifiers because they were originally used to perform mathematical operations. And the first op-amps were made out of vacuum tubes. In the symbol, in the schematic symbol shown here, you see the two inputs. The two inputs, one is called a non-inverting input. That is your Vin positive. Your inverting input is your Vin negative. So those are the two inputs which will be taking signals, and the op-amp will operate on the difference between those two inputs. Pin 7 is your positive voltage supply. That is often referred to as your VCC. Pin 4 is the negative voltage supply, and that is typically referred to as your VEE. And then pin 6 is your Vout. Now, this is for an 8-pin type of an IC package, which is shown towards the right. The op-amp comes in many different packages. Just to illustrate this, on this slide towards the left, we see a symbol, a drawing of an 8-pin dip package. And then towards the right, we have a 14-pin dip package, but this one here has 4 op-amps in it, while the 8-pin package only has 1 op-amp inside of it. So the one towards the right, because it has 4 op-amps in it, it's called a quad pack. A quad pack, and so therefore it has 4 op-amps inside of it. Shown here is the internals of the LM741. The LM741 is a general purpose operational amplifier. It's an entry-level amplifier that is used to basically teach with for a lot of hobbyists and so on and so forth. The cost of this chip is fairly low. I believe it's maybe about 20 cents or so. But this is what is inside of this particular chip. It has a lot of transistors, and it has a bunch of resistors, a capacitor, as to what's shown here. Now, this is very particular just to the LM741 and not a different op-amp. The LM741, as far as the package, an 8-pin dip package, is shown here, and the pinout for the chip is also shown. One of the things that I do want to bring a point out to is basically that it has a bubble, or kind of like a half moon on one end of the package, and that half moon right there, when you look at the orientation of the chip, if you place that towards the left, then the bottom left will be pin 1, and then you count counterclockwise all the way around. So I will illustrate that. Here in the diagram, we have this half moon. That half moon is seen right here on the chip. And so therefore, if you orientate that to the left, then the bottom left is pin 1, which would be right there, and then you count the pins counterclockwise. So that would be 2, 3, and 4, and this would be pin 5 up here, then 6, then 7, and then 8. The pin out of the IC chip also has some pins that are for the offset nulling of the operational amplifier, and this is some pins that allow you the functionality to adjust the output of the op-amp to be biased exactly at 0 volts. In reading this, it says, due to the different bias currents that may be presented at the inputs due to the front-end transistors of the op-amp, a differential voltage may present itself and therefore give a non-zero voltage output, even if the input to the op-amp is 0 volts. A nulling circuit allows the output bias voltage to be adjusted to 0 volts. Let me illustrate this. Let's draw an operational amplifier symbol here. We have our inputs. I will call this my V in, and this is my positive. This is my V in negative. And I have my V out pin. I have my positive voltage supply pin, which is VCC, and my negative voltage supply, which is my VEE. Again, this is the positive of the supply and the negative of the supply right there. Now, with that stated, let's look at how I would create a voltage supply for the op-amp. And it's simply putting two voltage sources in series, something like this, and let's assign some values for VCC and VE. Let's say that this had plus 10 volts and the VEE was negative 10 volts. So we have a bipolar power supply. So therefore, what I would do then is make these voltage supplies 10 volts each. The top here would provide me my positive 10 volts, and that's if I forced this point to be ground, and if I did that, then this point at the bottom would be my negative 10 volts. And from there I would just connect it in such a way, and your V out, which is right here, would have a resistor which connected it to ground. And that's how we're able to supply the op-amp with a bipolar power supply. Now, because of that, your V out will be having a bias voltage that is at 0 volts. But even though it's intended to be at 0 volts, it might be just a little bit off. So the offset null pins can be used to get it to be exactly 0 volts. Now, let's look at a plot right quick. And here's my plot. And let's say that we were amplifying a sine wave and the output was something like what's shown here. So therefore, the positive side of the sine wave, that's going to be handled, all of this is going to be handled by the positive voltage supply, which is your VCC. And all of this other side here is going to be handled by the VEE supply, which is negative 10 volts. So each of the supplies has is contributing to creating the proper output. So both the positive and the negative supplies are needed. And of course that would provide a V out that's biased at 0 volts. So the offset null pins are used to adjust this to be exactly 0 volts right there. One other point to make is that your V out can never exceed the voltage supply amounts. That means that the peak, that this very peak right here, the very top of the signal, can never be greater than what your VCC is. So if your VCC is plus 10 volts as shown in this diagram, your V out can never exceed that. And for VE, the exact same thing. That is going to be the constraint for your V out when it goes negative. In other words, when your V out goes into the negative realm, it can never go lower than negative 10 volts or whatever your VEE is. So for example, if we were to say that this op-amp had such a large amount of amplification and we were amplifying a sine wave, let's say that the sine wave did something like this, but this was here positive 10 volts and this here was negative 10 volts. And so as it's amplifying, at some point it's going to clip right there. Then it may come down, then it may do that, and then it might clip right there and then go back up, something like this. Well, what's happening in these regions right here, right there and right here? Well, that's where the op-amp is saturating. That it's amplifying it so much, but because the output has reached the maximum that it can go, the op amp is in saturation at that place. So this right here is in saturation, but this is in positive saturation, and this region right here, it's in negative saturation. Let's look at the ideal op amp. As far as the voltage gain, for the ideal op amp, we would say that it would have infinite voltage gain. But from a practical perspective, it has a gain more like about 200,000. Now, this is what we would refer to as open loop gain. So, without any components external to the op amp to restrict the amount of gain, it's going to have open loop gain. And in most instances, it's going to be somewhere about 200,000. It could be maybe 300,000 or something like that, but it's going to be a lot. One of the things about the ideal op amp that we would also like to have is an infinite input impedance. Op amps do have a high input impedance, but it's more like somewhere between maybe 2 megohm up to about 50, somewhere around there. So from about 2 megohm to about 50 megohm. Now that's going to be directly dependent as to what type of transistors are at the front end of the operational amplifier. One of the other things that an ideal op amp that we would like to have is a zero output impedance. From a practical perspective, most op amps are able to supply currents up to somewhere about 5 to about 25 milliamps. So in most instances, they are able to drive whatever load you attach to them. And also, one of the things that we would like about the ideal op amp for it to have is an infinite bandwidth, meaning that it could operate at any frequency. From a practical perspective, op amps do have a limit as to how high they will actually go as far as be able to operate at a frequency. So therefore, in most cases, op amps will only be limited to a few megahertz. Now, one of the other things that is mentioned here is the slew rate. Slew rate is usually going to be underneath, or within, I should say, about 0.5 to about 20 volts per microsecond. That basically just tells you how fast the output can actually move. As the output is changing, as the amplifier is amplifying, the output is changing based on the changes that are occurring at the input. And if the frequency is being increased, where it's going faster and faster and faster as far as how it's changing at the input, the output needs to keep up with that change. But this is one of the things that's going to limit, how well the operational amplifier will operate. You have some op amps that are towards, the bottom of that range, which would be close to about 0.5 volts per microsecond. So they can only move 0.5 volts per microsecond. So it's going to only be able to move that fast for that amount of time. While others are able to move up to 20 volts per microsecond. So hopefully it's apparent that the higher end ones, the ones that are able to move up to 20 volts per microsecond, that those are going to be the ones that will operate at higher frequencies, and therefore it's going to make them also more expensive. Now, we were talking about open loop gain. So this open loop gain is going to amplify any amount of difference at the inputs. But even though you might have a gain that's really high, because we had stated previously that open loop gain is somewhere about maybe 200,000. So therefore, even if the signal between your two inputs is very, very small, having a gain that is so large is really going to cause the amplifier to saturate. And the reason it's going to saturate is because the output can never exceed the voltage of the power supplies. So whatever your VCC is, whatever your VEE is, the output can never exceed those voltage values. So therefore, if you're amplifying a signal and you're amplifying it by something like 200,000, therefore, in most instances, it is definitely going to saturate. But it's saturating because the output cannot rise to a voltage that's very, very high. And again, why? Because the thing that's going to limit the actual height of the output is your VCC and your VE amounts. So here in this graph right here, we can see that we can get into what's called positive saturation, and we can get into negative saturation as well. Now there is a slanted line right there, if you see that, and that slanted line right there, that's more where the op-amp actually works as an actual amplifier, where you're actually controlling the amount of gain, where you have possibly a gain like 2 or a gain of 5 or a gain of 10, something of that sort. But this is where the amplifier is actually having control gain and is working as an amplifier as what we would think it would be. And so that right there is the linear region of operation to work where you have a control on the amount of gain. Anywhere else on that graph, it's going to be in saturation. And I just want to make sure that this is pointed out, so I'm going to put this so that I can draw onto it. So if we were to draw an operational amplifier one more time, we have something like this. Have our two inputs. We have our Vin plus, we have our Vin negative. And let's say that we were to put a voltage at this input. Again, the operational amplifier will be working on the difference. But because it does not have any sort of a control on the amount of gain, it's really running what we call, again, open loop gain. So therefore, it's going to be a gain that's very, very, very high, again, about 200,000. So even if it's a small amount of voltage, say it's a difference of 0.1 volts between these two inputs right there, you can see that 0.1 times 200,000 is going to give you a value something about 20,000 volts at your output. Well, obviously your output cannot rise to a voltage level of 20,000 volts, mainly because, well, one is the voltage supplies are not going to rise up to that level. In most instances, you're going to have something that's going to be a lot less. And so if we were to assign a value, say that your VCC value is plus 12 volts as an example, and your VEE is at negative 12 volts, that means that your output can never go higher than positive 12 volts or lower than negative 12 volts. So if we were to put a signal in here that has a difference of 0.1 volts between your Vin plus and your Vin minus, and that gets amplified, say something again like 200,000 times, it's going to cause the output to go into saturation. So depending as to which input is higher than the other will depend as to which way it will saturate, and we'll talk about that just in a bit. But the thing is this: when you're running open loop gain, the op-amp will have to be in saturation at your output. Now the question is it going to be in positive saturation, which is here, or is it going to be in negative saturation, which will be right there? And again, this region right here, this is the linear region. This is where we actually are able to put external components on the op-amp to control the gain so that it does not saturate, and therefore we can use it as what we would actually term an amplifier. Well, back to open loop gain, this is where the op-amp is allowed to operate at its maximum gain, and the gain is so high that even a few microvolts difference at the inputs will cause the op-amp to go into saturation. The output response is predictable though, so this is the thing that we can anticipate what the output will, or where it will be saturated at, by knowing these two statements. So the first statement here, it says if Vin plus is greater than Vin negative, then the output will saturate to VCC. If Vin negative is greater than Vin positive, then the output will saturate to VEE. And when you're running open loop gain, as was stated earlier, you are primarily going to be using this as a comparator. And for any other application, feedback will be used. So let's talk about the op-amp being used as a comparator so that we can show how we can predict what the output will be. Let's draw an operational amplifier. And we have our two inputs. We have our V in plus, have our V in negative, have our V out. We have the power supply pin VCC and the negative power supply pin, which will be VEE. And let's just assign some values here. Let's say that this is at positive 12 volts as far as VCC, and VEE is going to be at negative 12 volts. Now, the thing is what is happening at the inputs? We have to know what those values are to predict what the output will be saturated at. And so if we were to put some values here, we need to compare as to which one is higher, which one is lower. The easiest way to analyze this is if we were to draw a vertical line, and we were to put values on here. On above 0 volts, we'd have positive 1 volt, positive 2, positive 3, positive 4, and so on and so forth. And below 0 volts, we would be in the negative region. So this would be negative 1 volt, negative 2 volts, negative 3, negative 4, negative 5, negative 6, and so on. Now, the voltages at the inputs should be compared according to the scale as to which one is higher. Okay, obviously, okay, if you were to put this in a vertical sense, where it's coming up off the floor, for example, or if it's mounted on the wall, you could definitely then see which voltage is higher than the other one. So for example, if I was to put positive 2 volts here and say negative 1 volt right there, we could say, well, where is positive 2 volts? Well, positive 2 volts is right here, and negative 1 volt is right here. Now the question is, if this line here was actually in a vertical sense, all right? So therefore, if it was in a vertical form or a position, which voltage is higher? Well, hopefully it'd be apparent that it'd be positive 2 volts. That positive 2 volts is higher. So therefore, whichever input is higher, that's where it will saturate at. Since we're at the positive input, since the plus 2 volts, which is higher, is at V in positive, then your V out will be in positive saturation. So with those two values being inputted to the op amp, the output will be at positive 12 volts at the output. It will saturate in a positive sense. Let's take a look at two other values and see what's happening there. Let's say that we have negative 4 volts and we have negative 3 volts. And again, we need to compare them. Well, negative 4 volts is down here. Negative 3 is down here. Again, placing this line in a vertical position, which one is higher? Well, that would be negative 3. Negative 3 volts is higher. Well, negative 3 is where? We're at the V in negative input. So that means because we're at the negative V in input, it's going to be in negative saturation. So this would be at negative 12 volts then. Let's try another input. Let's try negative 2 volts here and positive 2 volts right there. Again, where are these values on our line? Well, negative 2 volts is right here and positive 2 volts is right there. Again, if we position that line in a vertical position, which voltage is higher? Well, it's going to be positive 2. So that positive 2 volts is connected to your V in negative. So therefore, you're going to be in negative saturation. So this is going to be at negative 12 volts output. To reiterate, the output response is predictable. Again, what the statements say is if your V in plus is greater than your V in negative, then the output will be saturating to VCC. And if your negative V in input is greater than your V in positive, then the output will saturate to VEE. Now let's take a look at closed loop gain. Having a closed loop gain is providing part of the output back to the input. So this is what's called feedback. So we're taking some of the output signal and feeding it back to the input. And there's two types of feedback. One is positive feedback and the other is negative feedback. So under positive feedback, as information is fed back, the output destabilizes, causing the op-amp to saturate, mostly used in comparator circuits to provide hysteresis. So when you see positive feedback, the op-amp is going to be used as a comparator, but it's going to have hysteresis. That's about the only type of an op-amp configuration that you could have with positive feedback. With negative feedback, as information is fed back, the output becomes more stable, causing the output to stay in the desired range. Amplification, filtering, and buffering circuits use negative feedback. With the diagrams on the bottom, looking at the leftmost one, we see where we have no sort of feedback. We're not taking any of the output at Vout and feeding that back into one of the inputs. So it does not have feedback, so therefore it's open loop gain. Under positive feedback, in that circuit, we can see that we're taking some of Vout and through resistor R2 are allowing some of that signal to be fed into the positive input. So that's why we call it positive feedback, because it's going into the positive input. When we look at the last circuit, the one on the right, we see that some of the Vout, some of that signal at Vout is being sent back through R2 to the negative input. So therefore we have negative feedback. As we were talking, when we have positive feedback, it provides hysteresis. It provides an upper threshold voltage called VUT and a lower threshold voltage called VLT that the input must exceed in order to affect a change on the output. The difference between VUT and VLT is called the hysteresis voltage, and the output will be either in positive saturation or in negative saturation. So why is hysteresis needed? Well, here in the top diagram, we have a comparator which is being used, and we have a sine wave, and we have a green dashed line. Those two are the inputs. So the comparator has two inputs, and one is the dashed line, and the other one is the sine wave. The output is the blue square wave. And so whenever the sine wave crosses the green dashed line, whenever the sine wave goes above the green line, the op-amp will saturate in a negative form. It'll go to negative saturation. And whenever the sine wave goes below the green dashed line, meaning that the voltage of the green line is greater, then the output will go into positive saturation. But the question is then, what happens if there's noise in the sine wave? When there's noise in the sine wave, you can see in the second diagram where the sine wave can actually fall back under that green dashed line. That's what the sine wave is being compared against. That green dashed line is a fixed voltage amount. So therefore, if there's noise in the sine wave, it can actually dip below the green dashed line, and therefore it'll actually cause false triggering, and so you can see what the result of that is. So noise is going to cause false triggering, or in other words, just noise is going to affect what the output does. And by providing hysteresis, we're per se reducing the effect of the noise, and in most instances really you are eliminating it. So taking a look at the last or the bottommost diagram here, you see that you have three green lines, three green dashed lines. The top dashed line is what we call your VUT. That's the upper reference voltage, and by calling it VUT, it's the upper threshold voltage. That dashed green line that's at the bottom, that's the lower threshold voltage, and the one in the center, well, that's just a center amount. Now, the way that this operates is when the sine wave goes in, and even though it has noise, it has to traverse all the way and go above the upper threshold voltage to affect a change at the output. And you can see that when the sine wave goes above that top dash green line, that's when the output changes state. And then, even though there might be some noise causing it to dip underneath that top green dash line, it will not affect a change until it goes below the bottommost green dash line. That's when it'll affect a change at the output. So therefore, what happens then is that you have a much smoother output in that it's responding, okay, the way that you would want, regardless of the noise in there. So in a sense, what hysteresis does, it basically eliminates the noise problem, because there's a range that the input signal has to travel through before you see a change at the output. Previously, it's just as soon as it goes above, you see a change, and as soon as you go underneath it, you'll see a change. But now it's not, no, you have to go through a range, okay, which is the hysteresis voltage, which is your VUT minus your VLT. So let's have these two lines be our upper threshold voltages, and this is going to be your lower threshold voltage, so that's your VUT and VLT, but together that creates your hysteresis voltage, and your V sub H is equal to your VUT minus VLT. That's a U right there. So if you have a signal then, and say if you have this sine wave, something like this, okay, when will you see a change? Well, let me draw the output as a orange line. So therefore, again, the input, okay, is going to have to go above your VUT to see a change. And in most instances, what will be is that you'll actually have the output going to negative saturation at that point. Then it's going to have to drop below your VLT, which would be right here, before you see another change right there. And again, your input signal has to go above your VUT to affect another change, which will be right at this point right here. And then it has to go underneath your VLT to affect another change right there. So even though your sine wave may have noise in it, and so even though it might have a little bit of noise right there, the thing is it has to travel this amount of distance. It has to travel, well, the distance of V sub H in order to affect a change. So even though you might have some noise, as long as the noise is smaller than your V sub H value, then it will not affect a change at the output. So here we have a comparator with positive feedback, and we're asked to calculate both the upper and the lower threshold voltages for the circuit. So let's do it. So for this circuit right here, we have a VCC that's equal to positive 12 volts, and the negative 12 volts is our VEE. Now, if we look at the output right here, we can see that we have an arrangement of resistors. Right, so here's our V out, but you can see that the V out, we have what I'll call R1 and R2 right there. And perhaps maybe I should rename these. Let me call this one R2 and this one R1. And the reason I did that is because some equations that you'll find out there in textbooks and so on and so forth refer to them as such. All right, so I just want to make sure that what I put down pretty much coincides with what you might find out there in case you run into a textbook or something like that online. All right, so we have R1 and R2. Now, one of the things that we have to remember about the op amp is that it has a very high input impedance. So current, as far as current here at Vn, okay, there will be no current going into the input. So there's no current flowing in there. And any current, okay, or is there any current going into the positive input? Well, again, currents do not go into the inputs of an op amp because why? Well, because the input impedance is so high, we will assume that it's zero, so current does not flow in there as well. So again, remember that aspect of the inputs, that current does not flow into them. Now, I am going to remove these to just unclutter things here. So current will not be flowing into the input. So we take a look at V out and say, well, if V out is in positive saturation if we assume, because what we're trying to solve for is VUT and VLT, these two terms, right? So VLT and VUT, we're trying to solve for those. When you're solving for VUT, the upper threshold, you will make the assumption that V out is at positive 12 volts. So at positive 12 volts, you are solving for VUT, right? So for the upper threshold voltage, we'll assume that V out is at positive 12 volts. And if you're at positive 12 volts here, and you have R2 and R1, we have current flowing down to ground. And so therefore we have an arrangement that looks something like this then. We have our resistors, have our ground, we have plus 12 volts here, and we have our 5K ohm, which is our R2, and we have our R1, which is our 10K ohm. We have this arrangement. Now the question is, what's going into Vin is being compared against the voltage at this point right here. Vin is being compared against the voltage that's being created by the voltage divider, which is comprised of R2 and R1. So really, what is the voltage at this point? What's the voltage there? Well, we can use the voltage divider rule to figure that out. That voltage is VUT. So therefore, I can say that VUT is equal to 12 volts times 10K ohm over 15K ohm. So we do the math on that, and we get something like 8 ohms. Therefore, our upper threshold voltage is positive 8 volts because, again, it's a positive value there. Now, when you're trying to solve for your lower threshold voltage, know that this comparator is open loop, therefore it's going to saturate in a negative form. So let's do that then. We are going to be in negative saturation at that point. So let's use a different color. Let's choose blue. This is going to be at negative 12 volts. So when we're solving for the lower threshold voltage, the assumption is that you're going to be in negative saturation. So now we have negative 12 volts, and we will have current actually flowing the other way since we're going to be taking in current through there. But what we're still trying to solve is, what is the voltage at this point? What is the voltage right here? Well, we can solve for that. We can draw our arrangement, and this is our 10K, and this is our 5K ohm, and this is negative 12 volts, and we're solving for the voltage at that point right here. And so therefore, again, the voltage divider rule is something we can use, and we can say that your VLT, the lower threshold voltage, is going to be negative 12 volts times, and this is going to be $10K over 15K. Now, one of the interesting things about it is that you're going to arrive at the same magnitude that you did with your VUT, and that's because the power supplies here are the exact same value. You're at positive 12 and using negative 12. So you're using the same amplitudes, right? Or I should say the same magnitudes. The only thing that changes is the sign. So therefore, you're going to end up with pretty much the same magnitude, except you're going to end up with negative 8 volts. And I see that I put 8 ohms. This is incorrect. That is voltage right there. That's volts. So therefore, we will have negative 8 volts there, and over here was positive 8 volts here, so your VLT is negative 8 volts. So therefore, we've solved for this problem here. Let's work out one more problem in solving for VUT and VLT and the hysteresis voltage. On the last problem, one of the things that we didn't do was we didn't solve for the hysteresis voltage, but that's the difference between the VUT and VLT. Since the VUT was at positive 8 volts and the VLT was at negative 8 volts, the span between positive 8 volts and negative 8 volts is 16. So your hysteresis voltage would be 16 volts. Now, let's come up with another circuit here. This is going to be something like this. And we have our resistors, something like that. And this is your R2, this is your R1. And let's say that this is equal to 9 kilo ohms and that this is equal to 1 kilo ohm right there, something like this. And we have voltages here of, say, positive 9 volts and negative 9 volts. And we have our positive input being routed to the voltage divider circuit right there. And again, we're asked to solve for VUT, VLT. Again, when you solve for VUT, for the upper threshold, you will make the assumption that the output is in positive saturation. So if we're in positive saturation, we're going to be saturating towards the positive supply, which therefore we're going to be at positive 9 volts right there. And if we're at positive 9 volts, we're going to have current flowing down this way. Again, current does not go into the input, so there is no current going to the input. So all the current is just going through R2 and R1. So all we need to do is to find out what is the voltage at this point that my input right here is being compared against. So therefore, that value is VUT. So therefore, VUT is equal to, and that's going to be 9 volts times 1 k ohm over 10 k ohm. And that is equal to 0.9 volts. Now that's a positive 0.9 volts, so that's the upper threshold voltage. To solve for VLT, again, we are to assume that when we're looking for the lower threshold voltage, that it's going to be in negative saturation. So therefore, negative saturation would be negative 9 volts. Negative 9 volts right there. And now the current, of course, would be flowing the other direction. It would be flowing upwards. But the equation still would be set up the same way that we did for VUT. We would have, and again, we're using the voltage divider rule, we'd have negative 9 volts. And we're trying to solve for the voltage across here. So therefore, it's the 1 k ohm over all the resistance in that path, which is your R2 plus R1, which is 10K. So therefore, doing the math, you end up with a negative 0.9 volts. So therefore, what's going to happen is that the output is going to be switching on you whenever the input crosses either positive 0.9 volts or negative 9 volts. So your V sub H then, and I should place that a little bit lower. Your V sub H then is equal to your VUT minus your VLT. It's the span between both of those. So therefore we have what? 0.9 volts minus a negative 0.9 volts. So that's going to be 0.9 volts plus 0.9 volts, which equals to a hysteresis voltage of 1.8 volts. That's what your V sub H is. Now, if we were to plot it out, what would happen? Well, let's just say that we did have a plot here, and let's say that the top here would be at your positive 9 volts. This particular tick mark would be negative 9 volts. That's where the op-amp will be saturating at. And your Vin, let's just say that your Vin is a triangle wave. So let's just say that it's doing something like that, a triangle wave that's being sent in. So let's just indicate a triangle wave here. Something like that. Now, the VUT will be where? The VUT will be at positive 9 volts, which will be somewhere about maybe right there. So at positive 9 volts. And negative 9 volts will be somewhere down here. So negative 9 volts right there. So whenever your input goes above positive 9 volts, it's going to go into negative saturation. So therefore your output will be looking something like this. At this point right here, it's going to go down, and then it's going to stay there until it crosses at this point at negative 9 volts, goes back up right there. Then it does not change until you go above your plus 9 volt mark, which would be right about right there. And then it does not change again until it goes to negative 9 volts, which would be somewhere about right there. And again at positive 9 volts, which would be somewhere about right there. So that's what your output would be doing. Let's take a look at negative feedback next. This is where we're feeding a portion of the output signal back into the inverting input. This is the Vin negative. This cancels most of the differential voltage, making it very small, allowing operation in the linear region. The op-amp will do whatever it can to make the voltage difference between the two inputs zero. For analysis of the circuit, it can be stated that that negative feedback maintains both inputs at the same voltage. Negative feedback helps overcome distortion and non-linearity. It improves frequency response and makes properties predictable, independent of temperature or manufacturing differences. Circuit properties are highly dependent upon the external feedback network, thereby making it easy to control. The first amplifier, is the voltage follower. It's also referred to as a buffer amplifier or a unity amplifier. And if you look at it, we're taking some of the output. In a sense, we're actually having just a wire, from the output going into your Vin negative. So it's basically just a wire again from V out connected straight to Vin negative. Now, what does this do for you? Well, it provides you what's called a buffer amplifier. A buffer amplifier has a gain of 1, again a voltage gain of 1, so that therefore your V out is equal to your Vin, but it provides you a very high input impedance, and in this case it's going to be somewhere between 2 megs or starting at about 2 meg ohms on up. So the input impedance of the amplifier is very, very high, and the output impedance is assumed to be 0, and its main function is to provide oscillation at the output of the signal source. And due to the op-amp's high input impedance, very little power is drawn from the signal source, thereby avoiding loading effects. And towards the bottom right, we see that the output signal is exactly like that of the input signal. But again, the main purpose for a voltage follower is because it's being used as a buffer amplifier. A buffer amplifier will typically have a very high input impedance and have a gain of 1. Here we have a non-inverting amplifier. For the non-inverting amplifier, it will amplify, but it will not invert the signal. In a sense, you're just going to get a magnified version of the input. So if you look on the bottom right, we have the input signal and the output signal. You can see that the output signal is in phase, right, with the input. It's just amplified. And so what is happening here is that we are taking some of the output and we're routing some of that output back into the negative input. But because of the arrangement, again, we are taking the actual signal in the positive input, in the non-inverting input. So therefore, because we're taking a signal into the non-inverting input, it is able to amplify it from the perspective of it being a non-inverting amplifier. Now, the way that this works here, here's a couple of things to point out. One is that the negative terminal is held at Vin, so that the current R1 is equal to Vin divided by R1. And since the input impedance is very high, the output is the only point where current can be either sourced or sunk. Therefore, your IR2 is equal to IR1, and the voltage drop across R2 is IR2 times R2. And if Vin positive, or if Vin is positive, then V out is equal to Vin plus VR2. And if Vin is negative, then V out is equal to Vin minus VR2. So to go a little bit further with explanation, let's draw a circuit out. Before we do that, please note that there's an equation towards the top right. That is your V out. Your V out is equal to your Vin times what's inside of the parentheses. What's inside of the parentheses is the voltage gain. So you could rewrite that equation as V out is equal to V in times A sub V. A sub V is equal to 1 plus R2 over R1. Here we have the non-inverting amplifier. I'm going to redraw it just a different way. I prefer to view it in this fashion. So we have our V in right here. And let's just draw this where it goes to a voltage divider circuit, something like this. And that is grounded. And here is your V out. It's still electrically the exact same thing. That hasn't changed. So as I was stating, your V out is equal to your V in times your A sub V. So your A sub V, the voltage gain, is equal to 1 plus R2 over R1. But you can rewrite the voltage gain also in this fashion, where A sub V is equal to R2 plus R1 over R1. So that's also A sub V. So if you don't want to use the top equation, you can use that equation. Either one of those equations will still arrive you at the same voltage gain. Now, the thing is that we need to assign values. We absolutely have to. Let's say that this right here is something like about 12 kilo ohms, and let's say this is about 2k ohm right there. And let's supply it VCC values. Let's say it's plus 12 volts, and your VEE is equal to negative 12 volts. Now, such questions that could be asked of this is, what is the voltage gain? What is your A sub V? Well, A sub V, as was stated, was R2 plus R1 over R1. So therefore we have 12K plus 2K ohm over 2K ohm. So in doing the math there, we arrive at a gain of 7. Now again, gain does not have a unit, it's just 7. So this has an application value of 7. Now, if we didn't have the equation for a gain or to figure out V out, so say for example if V in was 1 volt as an example, positive 1 volt, then we could solve it a different way. But just going through the equation, if we want to know what V out is, we have the equation above that says V out is equal to V in times AV, right? So therefore we could say your V in is positive 1 volt. We have a gain that's 7, so therefore your V out would equal to a positive 7 volts. Now, the polarity here is very important. So anytime you're trying to figure out what your V out is, make sure you put polarity down, all right? That's highly important. If you don't put polarity down, it's going to be assumed that you're meaning positive, but if that's incorrect, you can see where that could cause problems. Now, what is the other way to solve this? Let's just say that we did not know the equations at all. We just wanted to solve what V out is, and say that we did have a positive V in, but we did not have the equations to figure out V out. Well, another way to solve this is by doing something like this. We can just use Ohm's law. We can just use Ohm's law. Now, one of the things that was stated is when we're operating, or when the op-amp is operating in the linear region, both the positive and the negative inputs, both your V in positive and V in negative, are going to be held at the same voltage. That means that if I supply positive 1 volt here, that means that your other input is going to be held at positive 1 volt as well. Means that this point right here is going to be at positive 1 volts. Right? With that information, then you can solve for V out. Since you have positive 1 volt and current is not flowing into the input, meaning that there is no current flowing in here, there's no current, so all the current has to be coming from V out. All the current flowing through here has to be going, or coming from, I should say, from V out. So if all the current is coming from V out, then we can definitely figure out V out, because we can figure out what the current is. And the way we figure out the current is by knowing what the voltage is across R1, and we know that already. It's positive 1 volt, because this side of R1 is grounded. It's grounded right here, and we have plus 1 volt on the other side, so the voltage difference across R1, or the voltage drop, is going to be 1 volt. So therefore we can figure out what the I is. The I value through R2 and R1 is equal, and again, if I look at it, I'm just going to call all this I, but really right now I'm solving for I by working with the voltage across R1. So I is equal to V over R. So the voltage is equal to plus 1 volt divided by the resistance of 2 kilo ohms, which is equal to 500 microamps. So if we know that the current flowing down through there is 500 microamps, then what is V out? Well, V out is the voltage across R2 and R1, and we know the current flowing through all of that is 500 microamps. So V out is equal to I times R2 plus R1. Right? So therefore I, we've established, is 500 microamps, and R2 plus R1 is 14 kilo ohms. So let's do some math. And it's equal to 7 volts. So whichever way you use to solve this, you still end up with the same answer, but I want to show you how to solve it using Ohm's law instead of relying on an equation. Okay, 50 microamps. Now, since we know the current flowing through there, let's see what the voltage drop across my 10K resistance across RF is. So the voltage across RF is going to be equal to I times R. So that's equal to 50 microamps times a resistance of 100 kilo ohms. And that equals 5 volts. So there's a 5-volt drop across RF. Now, please look at the way that the current's flowing. It's flowing through RF from right to left. So here we see that we have 0 volts. That means that the voltage on the other side of RF has to be greater by 5 volt. There's a voltage drop of 5 volts across RF, so that means that this here must be positive 5 volts. And that's the same result that we got through the equations. Here we have the summing amplifier. The summing amplifier provides for several inputs and allows the mixing of the input signals. For the above circuit, each channel provides the same amount of gain. Let's take a look at the equation. Now, one of the things that stands out here is that the inputs to the amplifier, or the input signals, I should say, are V1, V2, and V3. So in a sense, we could rewrite this equation to be more like this. We could say that V out is equal to negative R sub 0 over R1 times V1 plus V2 plus V3. So that equation would provide the V out value for your V ins at that instant times the gain of negative R0 over R1. Now, we could break that down even further. We could say that V out is equal to negative RO over R1 times V1 plus negative RO over R1 times V2 plus negative RO over R1 times V3. So that could also be stated in that fashion. Now, this equation here would be interesting, or I shouldn't say interesting, should be useful, or would be useful if the values of R1 would change. Now, R0, okay, or RO, is the same all the time. It cannot change because there's only one of them. But we could change the R1 values. We could rename these, for example, and instead of R1, we could call this one RA, call this one RB, and this one RC, for example. Therefore, we can come back here and say that the gain for that first channel, channel A, for example, would be your negative RO over RA. And your second channel, now this right here is the first channel, okay? And your second channel would be negative RO over RB. That's your second channel. And then negative RO over RC times your V3 would be your third channel. So you could have three channels with separate gains on them, so that you could adjust it, you could amplify one more than another, and really operate more like a true mixer. Now, we had been talking about that at some we could possibly operate an op-amp off of a single supply. Now, this can be done, but one of the things that needs to happen is that we still need to, at least from the perspective of the op-amp, still provided a bipolar power supply. So in a sense, we would have to trick it into thinking that it had a bipolar power supply. So that is something that could be done. Here on the slide, you can see that in most cases we would have the op-amp, and we would have both a positive supply and a negative one as well. That's shown in the diagram towards the left. But we could take an op-amp and configure it to work off of a single positive supply. But if you take a look at what's happening on pin 3, instead of it being grounded like we had in the figure to the left, the figure to the right has it that it has to have half of the supply. So that's one thing that has to happen. You have to supply 1/2 of the positive supply at your pin 3. So as is stated here towards the bottom, or the very last statement, it says that the reference for a single supply is not grounded. In most cases, the reference is biased at 1/2 of VCC. This non-zero volt reference is referred to as a virtual ground. The virtual ground is a reference for the input and output voltages, and the input and output voltages swing above and below this virtual ground. In most cases, the input and output will be referenced to the system ground, thereby requiring the use of decoupling capacitors to isolate the DC potential of the virtual ground from the input and output. Due to the decoupling caps used at the input and output, the only type of signal that the op-amp can operate on is an AC signal, meaning that the only signal that you can send into the input and be able to see at the output properly would have to be an AC signal because you have to have a capacitor at the input of the op amp and at the output as well. So we can create a virtual ground by using an op amp in itself. When we take a look at the op amp, this is actually a buffer amplifier. And because why? Because the output is being fed back into the inverting input. So this is a buffer amplifier. And really what is happening is it's taking the voltage from the voltage divider circuit, which is comprised of R1 and R2. So R1 and R2 are going to split VCC in half. So let's just say that VCC was 12 volts. So therefore halfway point is going to be 6 volts. So 6 volts will be going into the op amp, and it's going to provide a high input impedance and provide enough of a current output which will drive that 6 volts, okay, and be able to supply the current to any circuit which is attached to it. So you can see that the Vout is going to be at half of VCC, which, as we stated, if we allow VCC to be 12 volts, then the output will be at positive 6 volts. Now here we have a circuit for a non-inverting amplifier, single supply. We can see that the op amp itself has a VCC value, but that the VEE pin is grounded. So what has to happen? Well, if you remember that your Vout is going to be referenced to ground in a regular op amp configuration that has a dual power supply. And it'd probably be best to to draw this out. So our op amp might be something like this. And this right here is an inverting amplifier, excuse me, a non-inverting amplifier. This is a non-inverting amplifier. We have our VCC and we have our VEE. Now the thing was that this op amp, because it had a bipolar supply, we had a reference down here, and perhaps I should put that in a different color. We had the reference be grounded to 0 volts, which is halfway between VCC and VE. So if we had allowed VCC to be, say, positive 12 volts and VE to be negative 12 volts, halfway in between would be, again, 0 volts. So this point down here, okay, is going to be the halfway point. So therefore it's grounded, because why? Because 0 volts is the halfway point. But now what we're doing is we have an op amp that we want to use a single supply on. So we have something like this. This is still your R2 and your R1 right there. And you do have a VCC that's equal to plus 12 volts, but your VEE will be grounded. That's connected to ground now. So if you recall that the bottom of R1, okay, in the first diagram, which had a bipolar power supply, was grounded, but it was grounded at the halfway point. So this point here in the single supply circuit is going to have to be also at the halfway point. Well, what is the halfway point? Well, if you have 12 volts as your VCC and at VE you have 0 volts, then the halfway point between 12 and 0 volts is going to be 6 volts. So therefore, this point, which is the bottom of R1, has to be at the halfway point, which is 6 volts, which is equal to what? Well, 1/2 of VCC. It's 1/2 of VCC. So therefore, we can use the circuit that was shown. It's a buffer amplifier. So we have a plus and a minus here. And we are going to take the output and feed it back into the inverting input. And the non-inverting input is going to go to our voltage divider circuit, which is a value, and typically we use 100K and 100K. So that's going to split it in half, providing us with 6 volts, positive 6 volts. And a buffer amplifier, again, it provides a high input impedance with a lot of current at the output, but the gain is 1. So whatever you put in is what you see output as far as voltage wise. So therefore we're going to get positive 6 volts here, and all we would do is connect it right there. And now we can operate that op amp, right, with a single supply. Now, our 1/2 supply right here, which again we call this a virtual supply, is still going to have your plus 12 volts, but its VE will again be grounded. It'll be grounded just like that. And don't forget that in order to operate this, we're going to have to put a capacitor at the front end and a capacitor at the output right there. Now, one of the things that typically will have to be done here is because your positive input has some transistors, and again, it really depends on the op amp, but some op amps still have bipolar junction transistors at the very front end, and therefore they still need just a slight amount of current, even though from an analysis perspective we say that no current flows in, but from a practical perspective there is a very, very, very tiny current that flows in there. It's in the microamp region, so it's very small, but we in most cases would have to be putting a resistor here that's called a bleed resistor. This bleed resistor allows just a very tiny amount of current to flow through in order to bias the input transistors of the op amp, and this in most cases is going to be about 1 megohm right there.